Colin says, I am register. All right. The next topic that we are going to be talking about is registers and shift registers. So let's just, take a couple of steps back and see how we got to this topic. So we started with the latch, the simplest sequential element that would allow us to store one bit of information. And using latches and connecting them in a master slave configuration, we were able to design flip flops. And there were four standard types of flip flops: the JK, SR, D, and T. And what we are going to use mainly for registers is the data flip flop. That is what we are going to use in the case of registers, designing registers. What are registers? They are simply placeholders for bits. You guys remember digits? It is simply a placeholder for digits. So, why do you need registers? Why do you need temporary storage of bits? Well, suppose you want to track the outputs of a arithmetic logic unit, right? So suppose you're trying to subtract two numbers, and after you subtract those two numbers, you want to look at whether they are the same or not, right? Whether they are equal or not, and you're trying to find that out by subtracting them. There is a special output to the ALU, which is called the zero result. Zero result, there is a register you can have that will capture different flags. They can have flag bits. For overflow, you can have a flag. You can have a flag for zero result, positive result, unsigned result. So all of those things are essentially going to give to the user a quick way to understand what went on in the system. And registers are also used for a variety of other purposes as well. We are going to be using them to load things into a register. We'll see how we can read things in parallel from a register. We'll also see how we can shift contents of registers. Now, just to give you guys some idea about like shift registers, let me take a simple example over here. I have 1011, right? So if I have 1011 in binary, and if what happens if I shift it left by 2 bits, what happens when this is shifted left by 2 bits? I don't have any limitation on the number of bits, right? I can just shift left. So if I shift left, this guy is going to become 101100, right? I'm bringing in 2 zeros. That's right. What really happened here? From this to this, what really happened here? By multiplied by 4. That's exactly right. You multiplied by 4. Which is something pretty common, step that you have to do while executing instructions. When a CPU is working on instructions, this sort of shifting by 2 bits because you want to multiply a certain number by 4 is pretty common. And you can see that you would literally have to do a shift left operation for that. Now, if you do a shift right operation, instead of multiplying, you would be dividing by either 2 or 4 or 8. Any power of 2 you can divide by shifting to the right. And any power of 2, those many places you move left, you are multiplying by a power of 2. So something pretty common, and you will try to achieve that by using that shift register concept. Now this was simply moving things left or right. You could also have a circular shift register. You can also use shift registers for the design of counters. So at the end of this lecture, we will see how we can design a ring counter or a Johnson counter using this shift register concept. So a lot of interesting ideas at play here. But first, we will try to zone in into this idea that we can build registers using data flip-flops. Now, let me ask you this question. Why do you think we are using D flip-flop? Why not JK? Why not toggle flip-flop? What do you guys think? It is easier, okay, because D flip-flop is D flip-flop is not very cool. Actually, you know, honestly, when I learned D flip-flop, my teacher said data flip-flop, I said dumb flip-flop, because it was simply taking it whatever comes in and giving it out, right? Like it was it was not toggling, it was not interesting. Well, that was a few years ago, right? Like I'm talking about 15 years ago. Go ahead, please report it to the flip-flop police. um, all right, let me come back to the question here. Why do you think we are using a D flip-flop? Why not? Yeah, I know, sorry. It feels like yesterday. um Okay, so let me just answer it. It passes on the values. That's exactly right. I'm just holding it temporarily, right? Like I'm not toggling, I'm not setting or resetting. I'm just holding it temporarily for some time, and then I may change it later on, right? So that's the reason why I'm using D flip flop. That does not mean that I cannot design registers using the other flip flops. I could, but D makes the most sense over here. Data flip-flop makes the most sense for registers, the same way as toggle flip-flop makes the most sense for counters. So a storage register, what is it supposed to do? It is supposed to store data without changing it. Should you have the ability to change it? Yes. Whenever I want to change it, I can change it. I can change it all at once or one at a time. That depends on how I connect my clock input to those flip flops. And register files essentially are the register file stores a group of words of data. Classic LaTeX, yes. So if you have a register file, which means simply a collection of registers, those are placeholders for words of data. Right? A word is what? 32 bits, which is 4 bytes. We use the term word for 32 bits or 4 bytes. And you can specify which word to write or read from, right? So imagine like a collection of registers, and you can change or write to any one of them, or you can read from any one of them from that. In KNOS, which is Computer Architecture, Networking, and Operating System, we use a MIPS architecture. In that, the register file is 32 registers. So some of them are for saving some values temporarily or for a long-term use. Some of them are used for passing arguments. Some of them are used to store the stack pointer and so on. So that's kind of the register file that is specific to MIPS over there. Now, let us try to see how we can design a simple 4-bit register. So if you need 4-bit register, When you think of it, or try to lay out the register contents on paper, you will look at it like this, right? Four pieces, and those four entries will tell you the contents of the 4-bit register, and each of this can be a 0 or a 1, and I'm calling them Q0, Q1, Q2, Q3 because these are essentially the outputs of 4 D flip-flops. So the outputs of the flip-flops are essentially what the register has temporarily. And then you can change it, right? You can change it by connecting new things to the inputs and clocking them in. So for example, if I want to write a 1010 value into this particular 4-bit register, what should I do? I have 4 D flip-flops that are positive edge triggered. I want to write 1010 in this guy like that. What should I do? I actually need to do a few things, not just one thing, but I need to follow a steps. So Bennett says set the D's to the right values and wait for the rising edge of the clock. Perfect. That is absolutely right. 1010, right? So if I want Q3 to become a 1, I would need a 1 to go there, and a 0 to go there, and a 1 to go there, and a 0 to go there. Once I have set those values of D's and made them stable, right? I'm gonna make sure that I follow the setup and hold time requirements, and then I'm going to look for the positive edge on the clock. And as soon as all these flip-flops look at a positive edge on the clock at the same time, these are synchronous. They are going to load 4 bits parallelly into the register, making this 1010. You can see that? This is what we call a parallel load operation. You can also call it parallel in. The reason is we have loaded things into the 4-bit register all at once. We did not do it, one by one. All went in at once. If we were doing one by one, then we would have called it serial load or serial in. So here is another same picture over here elaborating the same sort of concept of using D flip-flops. There's a D flip-flop here, D flip-flop here, D flip-flop here, D flip-flop here. It is all connected to the same clock source. So all of them are synced to one timing source. And all the D flip-flops are also connected to a active low reset. Q looks... yeah, I know, sorry. There's an active low reset over here. What would happen if I make this a 0? What would happen to Q3, Q2, Q1, Q0? Those, by the way, are connected to a 7-segment display at the very end. What would happen if I make the reset signal go to 0? Yes, reset. So what would be displayed over here if I reset it? No, it's a 7-segment display, right? So it's a 7-segment display. So it should be just a 0. That's right. Yeah. Which also means that Q3 became a 0, Q2 became a 0, Q1 became a 0, and Q0 became a 0. But you guys didn't say anything about the clock. When you reset it, Do you have to wait for the active edge of the clock, or does it happen immediately? You don't know. Immediately, so that is the differentiation between a synchronous clock and a asynchronous clock. Asynchronous reset versus uh, asynchronous versus synchronous. Uh, how does the reset work? It is simply going to make zeros clock in to the outputs if it is a synchronous reset. But if it is asynchronous reset, then it has a mechanism inside which forces your cues to go to zero. So we'll see, slightly later how you can have like those special inputs put in. Is this do a reset in the SR latch? You would that's it's similar to the reset in the SR latch. Yes, but there is more to it. Just hang on. So what does this design do? It clocks in 4 bits in parallel, or you can use the active low signal, active low reset to make it all go to zero. This is what? This is your source, right? There's a 4-bit source. So you're taking 4 bits from the source, for example 1010, and you are connecting those things to the inputs of the D flip flops, which is D3, D2, D1, D0. And as soon as you have an active edge of the clock here, you will be clocking things parallelly into the 4-bit register. The first standard chip that we are going to talk about, which has this register implemented inside it, is the 74x175 quadruple, which means 4-bit data flip flop with a clear input. And right now, I suppose you guys are questioning whether this clear input is a synchronous clear or a asynchronous clear. And I'm going to tell you that it is a synchronous clear. The data sheet of this chip tells you that it is a synchronous clear, which means that it has to wait for what? For the active edge. What is the active edge? It is the positive edge of the clock. So it is not going to clear the flip flop, the register contents, until you see the positive edge of the clock. Now let's take a look at what are the inputs and outputs of this 74x175 chip. It is a positive edge triggered register. It has an active low clear. Can you see that? There's an active low clear. And I also said that it is synchronous, it is in sync with the clock. It has to wait for the next positive edge of the clock for it to clear it. And then you have a D0, D1, D2, D3, which essentially are going to function as 4 new bits that you can put into the register. Q0, Q1, Q2, Q3 are the 4 true form outputs of the register, which means essentially the contents of the register. And then you also have the complemented forms of the same outputs, Q0 complement all the way to Q3 complement. So let us try to clear it first. What do I need to do in order to clear my 4-bit register? No, there is no other reason. The other reason could be in order for, so if you see the same reason as um, cascading decoders, right? If you want to cascade decoders, then you want this active signals to be active low versus active high so that you can use them in interesting ways. So one guy responds when it is active low, the other guy responds when it is high. So it's useful to have a combination of active low and active high control signals. Let's see, send 0 to clear. Okay, so send 0 to clear, which means what? Let us try to connect this guy to a ground, right? If I connect this to ground, is it done? Will the outputs become zeros? Or and a 1 to a clock? Yes. I also need to wait for the next positive edge on the clock. So I've connected the clear input to low and I've waited for the next positive edge of the clock. And then what happens? All these guys become zeros. What about the other four? Need the rising edge on the clock. That's right. And then all the others will become a 1. Right? Do you see that? Color code this. So that is resetting the register, clearing the register. You have initialized it to a count of 0. Now let us try to have another example here, which is load a B in hex into the 4-bit register. What should I do here? Let us change this to a red color. B is 1011. Okay, so that's fair. B is 1011. So what should I connect to? So you guys are saying D0 should be connected to 1101, right? How about the clear? Can I leave it at ground? No, I need to connect it to high. All right, so let's me connect it to high here with a pull up resistor. Using red because that's the one that we did for that. All right, do I need to wait for the positive edge of the clock? Yes. And you have set the inputs. You have, isn't that still grounded though? Yeah. But I'm just showing both, like in different colors, right? Like I'm just saying blue was for the previous case, now it is the red one. You have made sure that the clear is not activated and you have waited for the positive edge of the clock. Those 3 had to be done. And when all of those happens, soon after the positive edge of the clock, through the propagation delay of this particular chip, your loading will be successful. So this will be 1, 1, 0, 1, and then of course this guy will be 0, 0, 1, and a 0. All right, you guys see that? Now, what do you think is going to be inside this? If you kind of have X-ray vision and try to look inside this 175 chip, what are you going to find? 4 D flip-flops. Yes, you are going to find 4 D flip-flops, right? They are the 4 D flip-flops which have D inputs, right? You have your what is that? We are calling it D0, D1, D2, D3, right? So you have D0, D1, D2, D3. There is no real significance over here. 4D, 4Q, 3Z, 3Q, and so on. So your new inputs are here, right? If you want to load new things, then you connect them to new bits into the register. Then you need to connect it to 1D, 2D, 3D, and 4D. everything is synced to the same clock. Inverted clock connected to negative edge triggered D flip flops, 4 of them. Uh, what is that? Why have that random not? What is it? What do you mean? Not. Is that yeah? So that was the question I was going to ask later on, but I'll ask it now. Fine. Why do you need this? So your clear underscore L is getting toggled. It is getting complemented, and it is getting complemented, which means that there is no change in the signal, and you're connecting it to all your clear inputs. Strong yes. So that is because you are connecting that particular signal to 4 things, right? So you may have an issue with the fan out, right? So you want to make sure that your logic levels are low enough versus high enough, right? So you that's why you have that buffer to get solid logic levels, because already it's connected to four things over here. What if this was connected to another chip with another four things over there? Then you would have trouble with the number of things in parallel. The more things you put in parallel, the voltage level will become lower and lower, because resistors in parallel will make a smaller equivalent resistance. So it is quite possible that you may not want to clear, but because you have connected too many things as the fan out, you may actually get to a low state and accidentally clear all the flip flops. That's why you have that there. Okay, let's come back. Uh, Everything is synced with the same clock signal, clock signal, clock signal, clock signal. The clock itself is an active high signal, but with the use of a NOT gate, you are converting that into a clock that can trigger negative edge triggered D flip flops. The outputs of those flip flops are again both in true and complemented forms: 1, 2, 3, and 4. So all your outputs are available in true and complement forms on those pins. Have a positive edge triggered design here, active low clear, 4 bits that you would want to arbitrarily load into the 4-bit register. And we know what goes on into this, right? You guys know what is inside this. You guys remember what is inside that? From last class? How many 2-input NAND gates are inside this guy? Anyone? We did the count last time. 5. This is a D flip flop. 12 was for positive edge triggered. 11. That's right. Because we can get rid of one. Because now we have kind of put it over here, right? So 11 2-input NAND gates in each. So that itself makes it 44. And then you have a bunch of transistors over here. You could also use NAND gates to get those done. Alright. So the symbol and the internal design showing you all the flip-flops over there. Next. The next chip is a 74X374 chip. Let's talk about its characteristics. The first thing that I notice here is the clock. What can I say about the clock? I can say that it is a positive edge triggered design. What does OE stand for? How is it not output enabled? That's right. How is it not 5 where? Here? No, no. So each D flip flop is made up of 2 D latches, right? There's a D latch here, there's a D latch there. Each latch, yeah, right. You got it. All right. Let's see. Positive edge trigger design, output enable, OE. Now, you guys remember where we used output enable signal uh, earlier? In what discussion did we see OE? Cascading. How about we say connecting multiple things together in the context of tri-state buffers, right? That's where we used the output enable, right? It was selectively putting the outputs in the high impedance state. It was when we were trying to share multiple outputs on the same line. That's where we are going to use that output enable even here. Earlier with the tri-state buffer, it was just one output. Now we have an option of disconnecting or connecting 8 bits at the same time. That's what OE is used for. It's an active low input in this case. Active low input. And then we have a bunch of inputs that you could use to load things parallelly into your 8-bit register, right? So let me write the title over here. This should be a 8-bit register. 8-bit register with output enable. You can load 8 input bits into the register at once. You can see 1D all the way down to 8D. You can use those as inputs to the D flip-flops, 8 of them. Have a positive edge on the clock, and as soon as you have positive edge on the clock, all of those guys will appear at the output over here. But then for them to be visible to you outside the chip, even the output enable signal needs to be low. Is the only reason you would use the previous chip for the inverted outputs. This guy? Right. So this is 4-bit register, right? So this is 4-bit register in which you have the option of using the synchronous clear positive edge designed register, and outputs are both in true form and complemented form. Yeah, clear too. Yes. And then this guy says, all right, I'm not going to worry about the clear. I'm going to make this sort of a connecting multiple outputs together exercise, right? So for example, if I draw this here, you can say if you had multiple of these, one, oh yeah, sure. And then you have another one here, right? And then you have a bus over here. There are 8 bits of this guy going here, 8 bits going here, the 8 bits going here, and then there is a 8 bits going here. These are all 74x374 chips, all of them. And all of this is 8 bit here, 8 here, 8 here, 8 here, 8 here. It's an input to the 374. So what you can do is you can use that output enable. Sorry. There is a OE, active low OE on all of them, right? So by using the output enables on each of these, and there could be many of them here, you can selectively put the outputs of all the 8-bit registers into high impedance except for one guy to go into the next level. So that's where this can be used. All right, let's see. 8, okay, and then now you have the other 8 outputs, but only in true form. Let me write some statements here. You have got 8 active high inputs here that are primarily used to load 8 new bits into the register. And then you have the outputs here, which are essentially what? 8 active high or true form outputs. True form outputs. And you can think of it like this. The outputs are going to tell you what is in the register. The inputs are going to allow you to put new things into the register, right? Like that's kind of what is going on here. Okay, let us try to do something interesting here. Let's say this guy is a 1, this guy is a 0 1 1 0 1 1 0 1, and then we have a positive edge on the clock. My goal is to write the contents of the register in hexadecimal form. What should I write? Contents of the register in hex form. What should I write in this case? Output enable is 1. OE underscore L is 1. Oh no, come on. This guy is 1. You have not enabled the output. High Z, yes. Everything is high Z. It is disconnected from the outputs are not connected to the flip-flops right now because output enable is high. It is an active low input. So everything is high Z there, right? So I suppose you can see that. Now let us try to make it 0. All right. Now I've made it 0 in blue. I've kept the same inputs 0 1 1 0 and all of that. And then there is another positive edge on the clock. Now what is going to happen? Let us see. B6. Let us see if that is right. So the way you would write it is what? 8 down to 1. So you would say 1 0 1 1 and then 0 1 1 0, right? So you've got a B there and a 6 there. So B6 in hex is absolutely the right answer. That's right. Also, something to note, we had to wait for the positive edge of the clock for this to happen. All right, questions about this? All right, let us talk about some other thing. There is there are other forms of octal registers. Octal registers simply mean it's a 8-bit register. The number next is 74x273. How is it different from the previous one? This has an asynchronous clear, which means that as soon as I clear, all my outputs will go to 0. It doesn't wait for the positive edge of the clock. Let me just, this is your, doesn't wait for next positive edge of clock. It does it immediately. As soon as you make it clear, doesn't wait for the next one to come in, it will make things go to 0. Is there any way to easily tell if it? No, there's not. Like you got to look up the data sheet of the component. It has to be given. There is no way to know that without knowing that. Positive edge triggered design, 8 inputs that you can load into the register. The outputs are in true form only as before. So outputs are over here used to see the contents of the register. Inputs are being used to change the contents of the register. So something very similar to what we have kind of seen before. The only difference here is that it has a asynchronous clear, but there is no output enable. By the way, wherever you see this OE, right, your mind should kind of latch on to the idea that, okay, this is with respect to connecting multiple outputs together, tri-state buffers, high impedance state, all of those ideas, wherever you see OE. All right, let's jump here. All right, the next one is 74X377. How is this different? Still has a positive edge trigger design. There is a enable for the clock enable. I am not going to remove my crystal oscillator from the design. I'm going to use an additional input called clock enable input so that I can selectively disable and enable the clocking source. That is your enable input there. And see how it is happening, how it is being used. It is active low, right? It's an active low input. So let's try to make it 1 first. And actually what I'm going to do is I'm going to try to observe what is going on in this one. Can you guys tell me what is going on in this one? This is one of my favorite components that we talk about in this class. 2 AND gates feeding into an OR gate. One of the AND gates is getting complemented form of a signal, and the other AND gate is getting the true form of the signal. It is going to be a what? Guys, what is the box thing? I thought this was an open shut case. SOP, NAND, exclusive or no, marks. Yes, marks. You see, there is a enable this guy going into this and the complemented form going into this, right? So if it is 0, it selects this guy. If it is 1, it selects this guy, right? It's a 2:1 marks. All right, let me just draw the 2:1 marks here. What is my select? My select is actually enable underscore L, an active low enable. And it could be a 0, it could be a 1, right? So let me just write that. It could be a 0, it could be a 1. When it is 0, what goes through? If it is a 0 here, it is a 1 here, it is a 0 here, right? That means this guy is out, this guy is in. So the output over here is going to be what? This is going to be 8D and 1, which is 8D. So D input, the input over here is going to be the most significant bit of the new thing that you want to load into it, right? 8D. So I should say 8D, your new input that you want to load into the register, goes through to 8Q plus. That is the next state of the flip-flops. Because once you make this available over here, you still have to, have a positive edge on the clock. Only then it will get clocked in. So 8Q will become 8Q plus. But when enable is 0, what happens? When enable is 0, let's do it in blue. When enable is 0, this guy is 0, this guy is 1. That means this guy is out, this guy is in. And at this time, your previous output is being fed back, right? That's right, store. Yep. So 8Q is coming back. So 8Q. Now think about this. If you enable your register, you can load new things into it, If you disable it, then whatever it was will continue to be the same. Hence, disabling the clock. You guys see that? So you have kind of added on this enable input here with the 2:1 marks to remove the dependence on the positive edges of the clock. So no matter how many positive edges you see on this clock, and no matter what you have on these inputs, these outputs will not be able to change until you enable your octal register. You guys see that? All right, friends, let us stop over here and we will meet again on Tuesday